Right. Well, welcome to the February 22nd meeting of Rose City Astronomers, our general meeting. February and March this year have the same exact calendar. So, and February is kind of a shortened month. And then we had the storms, so etc. So I just wanted a very basic business meeting here. Our membership continues to kind of grow steady, steady, steady. We're now at 687, last year 674, at this time in the year before 669. Um, our calendar, we have a telescope workshop coming up this Saturday. The next astro imaging SIG is Tuesday, March 2nd. We have Thursday night dinners and Friday lunches with RCA online. Our next meeting is going to be Monday, March 15th. And every year in February, our February meeting almost always coincides with the holiday in honor of Dr. Martin Luther King. And February is Black History Month. So for the last 5 years, I've honored that by mentioning the contribution of African Americans to the space sciences and to STEM. Originally talked about Mae Jemison, the first Black woman into space, and then Katherine Johnson, of course, the mathematician. And last year I mentioned George Carruthers, who was a NASA engineer who created what the press called a sniffer. It was a spectrograph of some sort that was able to detect gases and elements in space. And sadly, he just passed away on December 26th of 2020. Another loss of 2020. This year, I want to highlight the first three African American astronauts, class of 1978, Ron McNair, Guy Bluford, and Fred Gregory. And I also found a New York Times very good article that was written in 2019 about Ed Dwight, who was set to be America's first Black astronaut, but he wasn't because they redefined who could be an astronaut, and it defined him out. So he was we would have had African American astronauts in the early 1960s, but they required that they be test pilots, and that kept women out and a lot of Black Americans out. So anyway, that's my annual contribution. I think it's worth 3 minutes to spend time talking about the contribution of Black scientists to astronomy and space exploration. We have some club accomplishments, all in the form of earning Astronomical League awards. Louis Robita has earned 2 Astronomical League awards, the Lunar Binocular Observing Program and the Lunar Observing Program. Congratulations, Louis. I think this is, I encourage everybody who wants to be an observer to start with the lunar programs. It gets you some good experience. You learn to take notes. You learn to look carefully. You learn to find things. The moon isn't always as easy to find as you might think. And you can do it with binoculars. You don't have to own a telescope. There's a lot of overlap between the 2 programs. So if you complete something for one program, you can document it for the other program. Mike Grabner has earned both the Solar System Observing Program and the Great Conjunction Observing Challenge. And so did Mike Reitmeyer, also earned the Great Conjunction Observing Challenge. So Mike, what did you have to do for the Great Conjunction Observing Challenge? Turn your mic on.
So, sorry, I had to find the button and I had a dog bothering me. So you had to either sketch or image the conjunction, and you had to incorporate some level of outreach to it. So what I did is I frantically checked maps and weather forecasts leading up to it and ended up driving out to a truck stop in Hermiston and setting up my imaging gear and praying my batteries would last long enough. And naturally, a few curious folks came out. And so wearing masks, I explained to them what was going on. I showed them the view on my laptop. I pointed out Jupiter and Saturn in the naked eye and shared that with a few folks. And as coincidence would have it, a gentleman and his entire family drove out all the way from the north side of the Astoria Bridge trying to find clear skies.
Oh,
His
wow.
whole family came out, and he brought out his little 3-inch Mac Cassegrain or Maxitov, thank you, telescope that he'd just gotten, so he got to view it through an eyepiece. And I made sure that he and his family knew about Rose City Astronomers and what we do, and I gave him a postcard before we went our separate ways.
Thank
And,
you.
yeah,
Yay. Yay. Well, I'm just delighted that in spite of the shutdown and in spite of how kind of topsy-turvy things are, that we're still actually accomplishing things and getting things done and carrying on with our astronomical life. And I want you to know that the club is too. The RCA and RCA board members are in conversation and discussion with organizations from Portland, Oregon, regionally, nationally. We're expanding what we do, what we can do, and what we will do. We've got a lot of seeds in germination right now. I mentioned that at the last board meeting. We've got a lot of things that are just beginning to sprout up. So it hasn't just become sort of a monthly meeting and we're done. There's more going on, and I want you to have faith. We'll get through this, and things will be better. I'm done.
Great. Thanks, Margaret. So now we'll have our monthly sky report from Jim Todd. Hello, Jim.
Hey.
Oop.
Now,
Ah,
okay. How's that?
gotcha.
Okay. So good to see everybody again. And see, now we have power back, and sound like it was pretty widespread. But I'm glad everybody's safe and healthy. And so let's take a look at the sky report for the month of February. Okay, so it's a big excitement, definitely, in the month of February. So let's start off, first of all, we had the 50th anniversary of the Apollo 14 landing. And that was the time that most people will remember Alan Shepard hit a golf ball on the moon. And so that's probably the highlight of that. But for me personally, it was this, the Kitty Hawk, the command module. Okay, well, there's something more to it. Okay, it was designed by Rockwell, okay? And the engineer, the project engineer, happened to be my uncle. Okay, and he was the engineer behind the command module, William Todd. Okay, and he, I have to say, contributed to my strong interest in space science because he worked for NASA for years and years and years. And he was the engineer behind the shuttle piggyback on the 747, right? And so that, for me personally, is the highlight. He passed away a few years ago, but that's the memory I have for Apollo 14. And on February 2nd was Groundhog Day, right? But a lot of people know that it's actually an astronomical related event. Right? It's crossover day. Okay? So it marks the midway point between the winter solstice and the vernal equinox. And that is the Groundhog Day. It's not exactly to the day, but it gets people talking about it. They say, wow, we're halfway there. We're almost to the vernal equinox. And the other days are Halloween, Lammas Day, and May Day. Right? And then we had the full new moon on February 11th and the full moon coming up on the 27th, which is known as the snow moon. And it seems appropriate for the month that we've had here in Portland. We got the snow moon, right? And on the 11th is Chinese New Year's. And people out didn't exactly get out there and celebrate, because you recall that at that time it was pretty icy and snowy around that date. And then just talking about Mars here, and China's orbiter made the first step, got there first, got the snapshot of the red planet Mars. I'm sure there are going to be more coming. And then we also had a record-breaking event on the February 9th, where the crew broke the record on the as far as overtaking the command module at 84 days for a U.S. flight record. Now, I want to point out, you can't really see it on this monitor. That's Ed Gibson, from the Skylab 4. Ed Gibson was a former president of OMSI. Didn't last very long, but there's that OMSI connection. And then we had another orbiter that reached Mars. The Arab Emirate Hope was able to reach successfully the orbit of Mars. Could do a long orbital insertion and do high radar images of the surface of Mars. And then just announced, which I'm pretty excited about, they're going to launch a private rocket called the Clipper to the Europa. And so that was just announced, and it's going to launch hopefully in 2024. And they're going to study the Europa up close and look at the ice features and possibly look for water. And then there was this name that, like, how did anybody come out with this? They actually named an astronomical unit called Far, Far Out. Who come up with these things? That 132 astronomical units. And so they discovered something at a great distance, but far, far out. That's a good name. And then there was an announcement here that they looked inside of a very large cluster. And National Geographic Log 6397. But when they looked at it even closer, they realized there were several black holes inside of that cluster. So that was pretty exciting news too, when people were saying, wow, look at all those black holes. And then, of course,
and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy.
And the video just came out today.
Look at the ground.
And this was tremendous. I'm sure all of you have seen it now. There's the parachute.
Navigation has confirmed that the parachute has deployed, and we're seeing significant deceleration in the velocity. Our current velocity is 480 meters per second at an altitude of about 12 kilometers from the surface of Mars.
And then there's goes the heat shield.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
And then this was just a fabulous video. It was just so much fun to watch. I probably watched it 20 times. And so, don't you wish that all of the Mars orbiters had this kind of technology?
Converge, velocity solution 3.3 meters per second, altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface.
So it's able to slow down from 12,000 miles per hour.
We're coming up on the initialization of terrain relative navigation,
and then it starts doing the sky crane.
Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
And then finally separated.
There's confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Timing. EVA is nominal.
We have planning of the landing engines.
Then it started to get lower. Then
Actual
there's the
fact.
separation.
Velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
We're in safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
Getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
What an accomplishment. And we did a Zoom meeting with the RCA on that day. That was a lot of fun. We had close to about 87, 90, like what it is now. And I think that was really a great bright spot in that day to be able to watch the landing. So it was a lot of fun. It's good to see everybody born with a lot of smiles out there. And so there's some shot there, aerial shots that we're seeing of the rover going to the crater. And then we had this tremendous sky shot. This is one of my favorite. And this is just a great shot from the crane, right? And then we got the wheels. We see the rocks. You see the details could have been blown away. Okay? And then we got our first shot from the HazCam showing the landing. And it landed just to more or less the upper left from Curiosity. And I've actually had many students ask me already, does that mean that Perseverance and Curiosity could meet someday? No, that would be a long journey. It would take years. Okay? And so there's Jericho Crater. And I think that's an excellent spot because the 28-mile wide crater based on that millions of years ago was flowing with water. Right? And so we see a beautiful display of Elsa's ejection and deposit and sediments, and this was their target. And look how close they came. There's that little green dot right there. That is where Perseverance is, right there. And I would be eager to get over there and see some of the features there. And then this is actually the close-up shot of Perseverance on the ground. Okay? And then they came out with the 360-degree view from Perseverance. So what next? In about 30 days, once everything is all checked out, okay, and they get all the instrumentation working and calibrated and what have you, they're going to drop this little 4-pound helicopter. This is going to be the Wright brother moment. Okay? And so they're going to drop it and it's going to veer away a little bit from the location. It's going to sit there and try to power up his batteries with the solar cells. Right? And then what it's going to do, in about 30 days, you'll have its first flight. The challenge here is that the Mars atmosphere is 1,000 times thinner than the Earth. Right? So they designed this with the special blades and what have you that will be able to lift and come down. My understanding is that the helicopter has camera on board, and I've read another report it does not, but I believe it does. But this is going to be pretty exciting, and when they're going to finally get the first launch, kind of a Wright brother moment on the surface of Mars. I'd be curious to see how it handles, right? And so that will come in about 30 days or so. So that will be fun to watch, right? And it will basically be on its own. It's programmed to do certain things, move a little bit, but I'm sure if there's anything to be said, the way the video came out today, we should get some great shot of the helicopter in view from Perseverance. Okay. So congratulations to JPL and NASA. What a great job that was. Okay. So looking ahead, right? Right now we don't have much viewing for planets. It's pretty much Mars in the evening, and in the morning, Jupiter and Saturn barely getting there, but Mars is still present over there in the southwest. And on the day of the landing, the moon was just next to the planet Mars. Right? And then we got the full moon coming up on the 28th. The new moon is on March 13th. It's known as the full worm moon. And the object I chose for the month of February, as well as March, is what I call the heart-shaped cluster, Valentine's Day. Right? So I try to find something that relates to Valentine's Day. So there's a heart-shaped cluster, and this one, it's somewhat faint, but it's still fun to look at. And if you were to go over to Canis Major, Sirius, and go just above that, right, it's roughly in the neighborhood of about 6. It's a beautiful cluster of stars. It's one that I would recommend in viewing for the month of February and March. Sunspots, it's getting more active now. Look at that little jump right there, sunspots that occur. And we're moving from cycle 24 to cycle 25. We have a few spots there today and visible. Now we're seeing a little more activities of the auroras. And just, I guess, today or yesterday, there was some pink auroras that was seen high near the Arctic Circle. Right? And then for the International Space Station sighting, it will be visible from February 17th through March 13th. It's going to be pretty much evening object. And go to spotthestation.com and get the space station flyover sighting to be visible from Portland, but anywhere around the world. Okay, so not much for recommendation as far as viewing, and if we ever get clear skies next time, but we have some opportunities to take a picture of the moon and such. So with that, stay healthy, everybody, and we'll see you in March.
Thanks a lot, Jim. That was great. Our speaker tonight is Rob Brown. Rob is a longtime club member, optical engineer, and entrepreneur. He's also a unicyclist and a juggler. And maybe if you ask very nicely, he'll show you one or both of those skills. Please welcome Rob Brown.
Looks like you're on mute.
Yeah. Yeah, you're on mute, Rob.
Bottom left.
There you go.
I'm sorry, that was my fault for not being in full screen mode, apparently. I couldn't see the mute button. Okay, thanks, Mark, and thanks to the RCA for hosting me for this. It's really an honor, and I'm very excited to do this presentation for you. So I'm going to talk about how 3D printing has changed my approach to astronomy, how it changed the way I observe. And I wanted to, this is not a scripted talk, but I did write something. In fact, it's in the meeting invite, and I thought I would just reread it to you all in case you didn't see it in the invite. But it talks about me as far as an introduction is concerned. And oh, I need to share my screen. We rehearsed all this, and I better do that first before I go any further. Right. Okay. Share. Boom. Do we all see it? Anyone?
We got you, Rob.
Yeah,
Looks good.
Okay, good. Okay. All right. So intro slide is the very next one. Here we go. Oh, they're going slow tonight. There we go. Okay. So I've been an optics nut since I was a kid. It's a long story, but I did my share of burning ants in the sun and playing with prisms. I got my first telescope when I was 9 years old. It was a Meade 60 millimeter, and I still have it. I studied optics and physics in college and became an optical engineer back in 1988. I have worked primarily in head-up display and augmented reality technologies for over 30 years. I was hired by RCA member Bob Wood in 1990, and soon he convinced me to make my first telescope. Say hi, Bob. He's here. It was an 8-inch f9. Since then, I have made an 8-inch f5 and a 12.5-inch f5, rebuilding all three at least twice over the years. When Bob was given a 3D printer for Christmas in 2016, he started bugging me to get one for myself. I resisted his lunchtime temptations because I thought I was too busy to deal with a 3D printer. Now, I wonder how I ever got along without one. When my youngest son, Quinn, started showing a serious interest in astronomy about 5 years ago, we did a father and son project to rebuild his 8-inch f5. He won a Young Astronomers Award from the RCA for it. He later came up with a series of problems that needed to be solved, and this talk will show how his innovative ideas came together with the 3D printer to revolutionize my astronomy experiences. So this is how 3D printing changed the way I observe, and I will move to the next slide. So I don't expect everybody in this club to know what 3D printing is, and I'm going to spend some time going at a very high level as to what is 3D printing. I know there's a lot of people who are well up to speed with this, and in fact experts with it, but bear with me, make sure I'm saying it right, and we'll get this covered. So what is a 3D printer? Well, it is basically a robotic hot glue gun. It extrudes a plastic filament out of a nozzle, just like a hot glue gun does, but it's a very small bead, and it precisely controls the flow, the position, and the velocity of that nozzle such that you can print layer by layer on top of a build plate and create a 3D object. So that sounds pretty simple. By today's standards, this is really a mature technology. 30 years ago, it was. I remember Bob had a 3D printed something on his desk for years, and we were just like, wow, look at that. Well, here we are today, and we got them in our houses. So the cost of entry to one of these things is pretty cheap to very expensive. I have this printer here, which is the Prusa Mark III i3, and I bought it as a kit for about $700. The filament is cheap. The filament roll like this is about $20-ish, depending on what you're getting. You have to invest some time, like anything else. You got to learn what you're doing. But it's not hard to get up to speed. And in fact, if all you want to do is get a 3D printer and print stuff, you can get your print models online. I'll show one later from Thingiverse. And you just download the print files and send them to your printer, and you can have that object if that's what you want to do. Optional is doing your own designs in CAD, and of course that's where I am with this. And I say it's optional, but I think that's only from the standpoint of, well, if you want to try out 3D printing, but you won't last long if you enjoy it. You're going to get into CAD, I promise you. So telescope makers are rapidly adopting 3D printing, and here are some examples from our own club members, Bob Wood, who I just mentioned, and Don Peckham. And Bob here built an 18-inch telescope. He made a welded aluminum frame to hold the mirror, but then above that frame is the actual mirror cell that does the collimating and mirror support. And all those parts are 3D printed, except for the nuts and bolts. And I think that's just fantastic. It's like, man, you squirted plastic out of a nozzle and you're holding an 18-inch mirror with it. Now, it's a lightweight mirror, it's not a 50-pound mirror or anything like that. But my gosh, it's a way to build a cell. And he also roboticized this scope, so it's got GoTo on it with the SciTech stuff from Dan Gray. And I think everything you see here in red and blue is 3D printed. The gray stuff are the motors and or in this case, the encoder. I think there's a motor over here and some gears and whatnot. And he printed all that stuff and put it in his scope, and it works. It's just cool. Don Peckham, on the other hand, did something that looks extremely simple, but in its simplicity is this incredible elegance and beauty. Don gets credit for pioneering a version of a string scope that is called tensegrity, which is a very stiff and lightweight way of making a string scope. And one of the key elements in fact, maybe the key element, is that you anchor your strings in relation to your truss tube at a precise position such that when the strings are tight, all of the loads are transferred to the very top of the truss tube. And if these screw eyes are out of alignment, that doesn't happen. You get bending moments, and it's just not optimum. And Don wanted to get it right, and he finally figured out that, well, shoot, I can just make a 3D printed part, and those anchors are going to be down to a couple of thousandths of inch kind of position, I'll bet. And, wow, this was a very simple looking part, but there's a lot of thought that went into it. And that really impresses me as far as telescope making is concerned. For my own fun, I bought a set of optics from Surplus Shed, a 76 millimeter Maxitov. You get the corrector lens and the mirror, and really no instructions. And they say, okay, I put them together and, you'll have a scope. Well, I thought this is perfect for 3D printing because I printed everything, including the eyepiece holder, and I bought some Kellner optics from Surplus Shed as well. And it works, and it works so well that, in fact, I was going to put collimation screws in, and you can see them. Get my mouse back here. Where did my mouse go? There we go. You can see where the collimation screws would have gone. And I just didn't populate them. I said, you know what? I'm just going to glue that mirror in, glue that corrector in, and see what I get. And it works. I don't need to collimate it. So I was very happy about that. The 3D printer accuracy is certainly good enough for a 3-inch scope like this. And then the other thing I wanted to point out was that you see a lot of fine lines in these things. These are threads, and the 3D printer can actually print threads. And by gosh, I made a threaded focuser. So it's a helical focuser. You grab the front of this thing and turn it, and the whole scope focuses. I had to kind of grind them together to get it to go smoothly, but it works. If I really need a good thread, like an 832, I'll clean it up with a tap. But it's amazing now that what's started off as a kind of an R&D thing, and then turned into a way of making a rapid prototype that had no functional use other than showing you what the parts look like, is now printing structural stuff. And this is just the ultimate. So I mentioned Thingiverse.com. You go to Thingiverse, you can download all sorts of odd things to print, and you search on telescope, and the first hit I got was an 8-inch f6, entirely 3D printed except for the aluminum truss tubes, the optics, of course, and the nuts and bolts that hold it all together. And this is big. I mean, it's an 8-inch f6. There's a chair in the background, and what this guy has done is he's diced it all up into sections that snap together and bolt together for strength. And so with a little printer like mine, you can print some really big stuff if you strategize correctly as to how to divide them up and assemble them. So kind of the sky's the limit. How much plastic do you feel like extruding through your nozzle? So, all right. And the last, then I said, CAD was optional. I figured I should definitely show you what it looks like. I use Fusion 360 as my preferred CAD program. got some experience with SolidWorks, and SolidWorks is very difficult to learn, very powerful, of course, but I've done SketchUp. That was where I started, was with SketchUp, and it's a nice way to create some stuff in CAD. But when it comes to 3D printing, SketchUp just had all sorts of errors in creating the print files that were very hard to deal with. It was a very manual, time-consuming process. Fusion 360 just fits right in between there with incredible power, relatively easy learning curve, at least for me. And they have a free version, and off you go. So this is by the way, this is a 12.5-inch scope that the kids up at formerly Wilson High School, now Ida B. Wells Barnett High School. They have an astronomy club, and I've been mentoring them on telescope making, and we're going to build this scope someday. In fact, we started cutting the wood. We have all the optics, and then the pandemic hit, and it's sitting in my garage in a semi-finished state. So anyway, shout out to them. So, and then the last bit of software that you need to know about, no matter what you do with 3D printing, is you got to know that there's something called a slicer. And this is really, from a software point of view, where it all happens. So you create a bunch of objects. And in this case, I'm showing you the Quinsight, which I'm going to talk to you about in quite a bit of detail coming up. These are all the parts laid out on the print bed, and these all get assembled together into a final assembly when you're done. What the slicer does is it determines how many layers there's going to be in this thing, about 1,300, and it does cross sections, and it lays them down in order and figures out where the nozzle has to go on each layer to create this print. So the first layer will look like this, for example. So the nozzle physically has to deposit plastic down onto the print bed everywhere you see some sort of a color, and the colors mean something. In this case, the purplish here, magenta, is the actual part that's being printed, and green is what's called support material, and that's there to build up to a height at which then the part is overhanging, and you can't just print into thin air very well. Actually, there's techniques for that too, but you want to be careful about that. So support material will be built up, and then the part will be printed on top of the support material where it overhangs. And when you're done, you just crack off the support material and throw it away. So you really try to minimize your support material when you're designing for 3D printing. So there you go. And there's other kinds of printers that will print like dissolvable support material, which is kind of interesting. We have one at work. It's the size of a refrigerator and then some, and nobody here can afford it. But so there you go. That's the first layer. Here's the 522nd layer, and you can see things are building up. You can see that that support structure right here in green, getting those overhung areas. You can kind of see into here and into here, and you'll see that the parts are printed as hollow shells with webbing or reinforcing structure inside. And generally, you're not printing solid plastic, but you're printing a honeycomb structure, inside of a hollow part. And that gives it plenty of strength, depending on the application. You can, of course, control how much infill you're going to print and make a stronger part with more plastic and more print time, of course, as needed. So finally, at layer 13, 19, and 18 3/4 hours later, an entire Quinsight is showing up on my print bed, and it looks like this. Here's the first layer in the upper left photograph. Right after the print head finished that first layer, I snapped that picture. And then somewhere around layer 500-ish, you can see those parts coming together. And you can really see that internal webbing structure in this photo here, or actually in this photo here on the lower left. You see how that infill is being structured. So, and you can also see the support material on the inside of this that all just cracks away, and you have a nice smooth cylinder on the inside. So, okay, so that's 3D printing in a nutshell. It's a vast topic, and I know I went through it really fast, and that reminds me, I'm sure you're all used to this by now, but if you have questions, put them in the chat, and I'll cycle back around to them at the end, as we always do, and try not to overlook you. So feel free to ask questions, and if they're really slide specific, put the slide number in the chat as well, and that'll help me go back and answer your question if I need to pull a visual. So, all right. So now the next part of my talk, and there's 3 parts: the 3D printing, this next part, which is the inspiration and the innovation, and then the final part, which is really how it has changed my observing. And we'll get into some real astronomy before we're done here. So you diehard astronomers, there's some stuff here for you coming at the end, so stay tuned. Okay, this is my son Quinn, the inspiration and the inspirator of the QuinnSight, and he is demonstrating the very first and second QuinnSights ever built at the 2018 Oregon Star Party Telescope Walkabout. And if you've been to that Star Party, you know that it's a way for the telescope makers in the Star Party to go around and admire everybody else's work, and you get to talk about it, and people can ask you questions, and it's kind of, it's instead of having a judging competition thing, it's just a way of sharing, and boy, people get a lot out of it. And one of the rules is that you get to brag about what you've done, but you also have to say what you would have done differently. And I have a special slide on that at the very end. So yeah, I'm following the rules here of the walkabout. So here's Quinn. He's showing off the first QuinnSight, and this is a description of the problem that my son had. He was using his Telrad on his 8-inch f5 in 2017. This is the scope that he just built, got an award for, super excited about, and he has to bend over too far to line up his eyeball with this tiny field of view and this tiny little lens. And you all know what that feels like if you use either a red dot finder or a Telrad. You sometimes it just isn't comfortable. And so he was having some problems, and on the way home from that Star Party, he said, "Dad, you're an optical engineer and you make head-up displays, and I was just wondering if there's any way we could improve the Telrad." And I'm like, oh boy. So we had a nice long talk on the 4-hour drive home, and this is what he said. He said he wanted to move the pupil, or the place you view from, up high off the tube so that he didn't have to bend over as far, and he didn't have to crowd up close to the tube, you know, and get in this uncomfortable position. He wanted to have a large field of view so that long before he gets his eye into alignment with the lens and the field of view, he can actually pick up something in the head-up display combiner, which is the piece of glass you look through, pick up something that would indicate which way to move to get centered. He wanted a larger lens. The Telrad, I think, has a 25 millimeter diameter lens, and we were able to find a source for 40 millimeter diameter lens. They're actually 42, but we take off 2 millimeters in diameter just to hold the thing in place. So 40 millimeter clear aperture on that. That means that you just don't have to be as closely aligned with the optics to see something, and that really relaxed. Later on, he was, you know, pointing out that, well, gosh, you know, we got these 3 screws on the back of the Telrad, and one goes up and down, and the other 2 go at these funny 120-degree angles. Can we just make it go up, down, left, right? And that was like, yes, let's do that. It's just, you know, we're starting fresh. Let's try that. And the final thing was, by golly, you know, he knows he's turned off his Telrad, and he puts it in his box and puts it away. Comes back a month later, and the switch is in the on position. The batteries are burned out. Well, I think we've all experienced that. Those switches are just easy to bump. And so we took care of that and just made it ultimately a smooth knob that is effectively unbumpable once it's clicked into the off position. You just got to remember to turn it off. So in summary here, it took a fresh young mind to ask, why are we still doing it the hard way, and how can we do it better? And the result then, of course, is this thing. And I want to now make it really clear that this is not a sales pitch, although I'm selling these and you can buy them from my website. I'm doing this because I want to share with you how this innovation has changed my experience and how it's changing other people's experiences. And you know, I'm certain that there's people in this audience who are going to look at this and go, you know, I might try building something. And so let's go with that. So here we go. So what is the Quinsight? In case you don't know, it is a high performance reflex sight for astronomers. It's I think the only site that's really been developed with ergonomics as the priority. Therefore, the large lens, the large field of view, the funny looking tower shape, instead of being laying down along your telescope, it sticks up. And it just makes it so much easier to get your eye in the right place, along with some other nifty things like a dew shield that flips down. Of course, I mentioned the horizontal and vertical, or alt and as adjust knobs. And then this funny little thing down here, it looks like a little white, it's actually a little white nylon screw head. And I got to give credit to Bob Wood for this one. Why not make the reticle rotate? And so we did that. And so you can slide this screw around, and the reticle turns in space. And I'm going to show you the power of that coming up here. So in fact, I'm just going to kind of skip over this slide because I pretty much hit it all, except for the fact that, oh, well, I'm using PETG to print. It's a super durable plastic. It comes with AA batteries. You can get it with a Telrad base if you want, and I can make the base plate curve to match your tube. And there's that sliding knob with the diagram on it. Let's talk about, one more thing before I get to the sliding reticle. I didn't expect this to happen. Howard Banish got one, and he put it on the other side of his finder on his 28-inch scope. I'm not sure how big this finder is. I think it's like 60 millimeter. It might be 80. The way Howard used to use his Telrad was rather than climb up a ladder and try to point the scope, he would stand on the ground and look up through the combiner and get the Telrad to point where he wanted it to. And then he would move the ladder and climb up and look into the eyepiece and, you know, and zero in on the thing he was looking for, and then find it in the focuser or in the eyepiece of the main scope. It's a very practical way of doing it. So Howard's problem was that standing on the ground and you know, he's tall, but still he was a good 4 feet away from the combiner, and it's just really hard to try it. You know, if you've got a Telrad, stand 4 feet away from it and try to align your eye with the display so you see something. It's not easy. So he just went ahead and put it right where he kept his Telrad. The large field of view and the large lens has made it a lot easier for him, he says. But I look at this thing and I go, my gosh, Howard, it's so tall you can just lean over your finder scope and look in there and see it. He's like, yeah, I know. And he doesn't often have to do that, but sometimes he does. And it's sure nice not to have to climb down the ladder to go realign your scope. So that, I just thought that was cool. This is what the field of view looks like. 16 degrees is just about the size of Orion from Bellatrix up here to whatever that star is down in the lower left knee. I forget the name, but look at that. The Telrad is 4 degrees and it covers the belt of Orion and a little bit more. But we added, you know, a whole bunch, 4 times the field of view. And wow, what can we do with that? And that is the first change to how I observe. It's called pattern matching, and it's something that you already do if you have a red dot finder or a Telrad or whatever you use, you're pattern matching. But this is a little bit more. So this is a favorite object of mine, the Cat's Eye Nebula. It's up in Draco. And the Cat's Eye is in oh gosh, there's a good word for this. It's in a place that is just, it's an unfortunate place in that you want it to be where it isn't. And it's this, I see a line between this star in Draco and this star in Draco. And I think of the cat's eye as being along that line and halfway in between these two stars. But it's neither along that line nor is it halfway between. And it's kind of on a line from the star in the head of Draco to Polaris, but not really. And so I would have this challenge where I look at my star chart and I would say, okay, there's the object. I could put down a transparency on my star chart and, you know, get an idea of what that pattern looks like, and then go try to match it up in the sky. And, you know, if any kind of light pollution, I can't see these fainter stars, and, you know, I'll spend 10 minutes or more trying to find the darn cat's eye nebula. And it's because I can't remember, was it offset toward the head or offset toward Polaris or offset toward that star or that star, and by how much? And so then what you do is you put a clean sight there and look at this. You can rotate the reticle so that the crosshair is now parallel to the line between these two stars, and then offset in such a way that this star is kind of in the corner over here. And by golly, the cat's eye is in my field of view in a low power eyepiece almost every time now. So that is what I mean now by pattern matching and changing my observing experience from a frustrating one to one that's much more direct. I really like to be able to kind of dead reckon these objects and say, okay, I'm gonna create that pattern, put my scope there, and there it is. Of course, there's the star hopping method, and this is a little bit more detailed, but try doing this. What happens here is, let's talk about M87 in Virgo. It's another object that is tantalizingly close to where it should be, but isn't. And look at that. It's on a line between this star in Virgo and Denebula in Leo, but it's not halfway between, and it's offset a little bit. And by golly, how are you going to pattern match that one? Well, again, having 16 degrees, you say, oh, look at that. That object is darn near 8 degrees off of that star, and it turns out to be 2 degrees down. And you can get this information off your star chart, of course. If you then align the crosshair so that the horizontal line is parallel to the Earth's horizon, and the vertical line is parallel to vertical, or more importantly, the horizontal line is parallel to the azimuth motion of your scope, and the vertical line is parallel to the altitude motion of your scope, then of course, when you move your scope, it's going to move along these lines, which is really powerful, because now watch what happens. You say, I got to move 8 degrees over, and you move 8 degrees over, you move down 2 degrees, and there you are. Sorry, I couldn't animate that better, but that puts you right on that spot. And if there's stars to hop to along the way, so much the better. But at least you know where you're going, which quite often I do not when I'm trying to find stuff in the sky. So this helps a lot. You'll notice here that, well, okay, there's that star right out at the edge of the field of view, and I could just go ahead and rotate my reticle and, you know, get some other kind of pattern matching going on and do it that way too. So anyway, that's the experience for me. And either of those two ways seems to be useful. It kind of depends on the object and what star fields you have as to which approach you want to use. But both of them, for me, have been very much more powerful than pattern matching with a red dot or even a 4-degree circle. So there you go. Now, that's part one of how 3D printing has changed my observing experience. Part two came about thanks to Betelgeuse. And as you know, a little over a year ago, in the fall of 2019, Betelgeuse got dim. And boy, that was an exciting thing, just to go outside and see this very familiar constellation not look the same anymore. So Howard Banish loves to sketch, and he's very good at it. He has a rainbow optics grating that goes between the scope and the eyepiece. He just screws in like a filter does. And with this grating, he was able to see the spectra of Betelgeuse, sketch it, show it to his friends. I got to see it, and I was like, wow, that is very cool. I want that. How do I get that without shelling out a few $100? Well, I knew that because I had a 3D printer, I could make the housing for whatever this thing was going to be. And because I have the advantage of having spent 30 years in optics and doing holography is one of the main reasons I got into my job, I just happen to have a holography kit that you can buy online and make holograms in your home. In fact, when we get to Q&A, I might even be able to show it to you, a hologram, that is. And so I put those two things together, and lo and behold, I have an eyepiece spectroscope. And what this has done for me is changed every visible star in the sky from an object that was either a nuisance or just something that I star hopped from to something else to an actual target. So imagine that. Every one of these stars, third magnitude and higher in a light polluted sky, is now something that's actually worthy of inspection, not just looking at, but really trying to understand. And that is really just a game changer for me, even in light pollution. So I'm going to now cover what the optics are about inside of a spectroscope. And I'm going to try to keep it easy to understand, but it's kind of important because there's an ergonomic story here as well. Astronomy is done today with, you're either taking images or you're taking spectra or you're doing interferometry. And of those three things, images are fairly easy for amateur astronomers to access. Spectra are a bit harder, and interferometry, forget about it for now. But spectra are interesting because the spectroscope or the spectrograph is the tool that tells astronomers what redshift is. And if you don't know what redshift is, that's okay. You're probably new to astronomy. You'll know soon. This is a fundamental of real astronomy. So how does this thing work? Well, you start off with a telescope, and this could be a 10-meter scope. It could be a 2-inch telescope. It does the same thing. It brings light in from a star, and it focuses it to a point. And at that point, normally we'd put an eyepiece, but in a spectroscope, you set up a slit right there, and you allow only the starlight to go through, so none of the sky background comes through. And then the light goes out to an off-axis parabolic collimate mirror. It's a grating, and what a grating is a periodic structure of microscopic lines. When light goes and hits that grating, the blue wavelengths reflect at one angle, and the red wavelengths reflect at a different angle. That's called dispersion. And actually, diffraction is what the rays are doing. Dispersion is the fact that the red and the blue do different things. So then that light comes off another off-axis parabolic mirror, and that's the imaging mirror. And it brings those rays to a bunch of foci at the focal plane. So we got the blue rays focusing at one end and the red at the other. You put a sensor there, like a CCD camera, and you got yourself a spectrum. What you don't have is a nice ergonomic way of sticking an eyepiece into this thing and attaching this whole thing to your Dobsonian telescope, because it weighs several hundred pounds or even just a few pounds, and everything's off balance. And the eyepiece is off at some funny angle. The scope is pointing off to the left in this case, and the eyepiece is pointing off to the upper right. So what an ergonomic nightmare it is to actually make a visual spectrograph. You don't want to use a configuration like this, obviously. It's not compact, it's heavy, it's complicated, it's going to be expensive, and by the time you get done building it, you're going to be taking pictures anyway. So instead, for visual use, we're using a technique called slitless spectroscopy. And this is nothing new, but this is an explanation of the grating that you can buy that Howard used, an eyepiece spectrograph. And basically what happens here is light comes in from the objective, it hits a grating, and it diffracts. And the red diffracts more, the blue diffracts less, that's dispersion. If you want really high resolution, which means a lot of separation between the red and the blue wavelengths, then you're probably going to bend those rays off so far that you'll miss the eyepiece. And then you have to put a bend in your spectroscope. And now it's like, oh, shoot, now it's not aligned where you want it anymore. And, it just becomes another ergonomic drawback. So what they do is they make a low resolution grating that bends the light a little bit, disperses it a little bit, and keeps it within your eyepiece so you can actually see something. And I'll give you a number here. Don't worry about it. There's not a test, but typically these gratings are made at 100 or to 200 lines per millimeter on the grating lines on the surface here. So it's a very fine grid of lines, but it's not a high resolution device. So slitless spectroscopy has the big advantage that you don't have a slit that you align to. You just focus your star to a point and observe the rainbow coming out, but the resolution is lower. And also, because you don't have a slit, then all of the other light from the sky comes through too, and there's nothing you can do about it except go to a dark sky. So it's subject to the same light pollution issues that all other observing is subject to. So, okay, so what really gets us the high resolution that I'm after? And that turned out to be, I was in a very timely manner pointed to an article published by the Physics Astronomy Department of the University of Iowa, and there's a link to it here if you're interested. It describes what's called a grating prism or a grism. And what you do here is you make a grating that would send light off at a very high angle, at a very high dispersion, but instead of having the eyepiece tilted off at an angle, you put a prism in the beam and you bend the rays back. And the reason this works is because the dispersion in glass is very, very much lower than the dispersion in a grating. And so you get all the dispersion from the grating, and the prism is just acting as a ray bender. So, and there's a little dispersion, but it's negligible compared to what the grating is doing. So now the eyepiece is back on axis. It all goes into your scope like an eyepiece. And I've gone from a resolution of 200 to 500 and more than doubled the size of the rainbow in the eyepiece for the same eyepiece focal length. So that really makes a difference when you're trying to view these subtle features in the spectrum of a star. Now, okay, whoops, it went 2 slides instead of 1. Here we go. This is the layout of the specter. So it starts off actually with a Barlow lens that produces parallel rays of light. And to get that to happen, you have to push the Barlow lens further into your focuser than you normally would. So I developed an adapter that does that. If you have a 2-inch focuser, you can push your Barlow lens in just like an inch further, and that'll produce the collimated beam. The prime focus of your scope is right here, so that's where your stars would normally come to focus. That collimated beam then enters the prism, bends, hits the grating, and disperses back on axis. A focusing lens creates the focus spectrum over here, and a cylinder lens actually spreads the light out in the orthogonal direction out of the plane of the board here, so that instead of having dots, you have lines, which are much easier to see than a skinny little spectrum. So there you go. That's what the thing looks like on the inside. And now we finally get to the astronomy science part of this thing. And once I built this thing, and I was so excited about it, and Howard got his hands on it, and it was just like, oh my God, this is way better than the than the eyepiece spectroscope I've been using, and but there was no way for us to really communicate the experience that we were having. I went out and bought myself a small monochrome astronomy camera, the ZWO ASI 174 mm, and it's really just a guide camera or a planetary camera. But I needed monochrome because that was the only way to show a complete spectrum without any artifacts from the camera itself, and I'll explain that in a second. Let's look at some of the data here. I tried to play professional astronomer and make some graphs, but you know, this is just me being a nerd. Looking down the lower left, here's Vega. So Vega, bright star up in the summer sky, and you know, quite often it's the first thing I look at because I got to line up my quinsight. And then there it is in the eyepiece. It's too bright to look at. I'm moving on to something faint, right? Well, by gosh, let's take a minute. And instead of moving off to something faint, let's put in a spectroscope and look what we see. What you see here are the absorption lines of hydrogen in the atmosphere of Vega. And by golly, this is like the most fundamental thing about the composition of stars that anybody who's into astronomy ought to know. What is the universe made out of? Hydrogen and a little bit of something else, okay, as far as matter is concerned. And there it is. There's hydrogen just showing itself off in all of its glory in the atmosphere of Vega. So what we see right here, this line is the hydrogen beta line. And way over here is that hydrogen alpha line, which is so far into the red that my eyes don't really see it, but my camera could sure see it. I did this in 2 exposures to go all the way into the UV, and you can see all these lines in the Balmer series, if you know what that is, just fading off into an upper limit where you just can't have lines anymore, and it just cuts off. It's just, this is pure physics, man. I just love it. Then you come over here to a star called Eltanin in Draco, and it's not a blue giant like Vega is, it's something else. It's a red giant, by golly, and it's got a whole bunch of this other stuff in it. It's not just hydrogen, it's a lot of other things. And this is the kind of stuff that astronomers are very interested in understanding, and it's the tool that tells us what stars are made out of. It's also the tool that tells us how big stars are, how massive they are, whether they're spinning fast, whether they're moving away from us or towards us. And all this information can come out of a spectrum. So this visual spectroscope is just a little peek into the world of professional astronomy. And without doing anything quantitative, although I've tried to here, without doing anything quantitative, just looking at spectra, I'm now super excited to say that, my gosh, I can look at a star and get a general idea of what kind of star it is. And it's just exciting to me, as you know, after spending most of my life being into astronomy, to actually be able to do this. So that's my excitement. Altair down here is just kind of another Vega, another big BA, probably a B or an A type star. I'm not quite sure. Anyway, there you go. So now, I said photos don't do it justice, and this is what I mean. So Howard put his cell phone up to his eyepiece. He was looking at Arcturus. I'm sorry I didn't label it, but this is the problem that I'm faced with when trying to communicate my excitement about this stuff, is that cameras really only see 3 colors. They have red pixels, green pixels, and blue pixels, and you get a little bit of crossover between them, kind of, sort of, a little bit of yellow, a little bit of cyanish, whatever. And then the display on which you're looking at them only displays red, green, and blue. In case you didn't know, the monitor you're looking at right now is just a red, green, blue monitor. So how do you really show the colors that aren't red or green or blue? What about the deep, deep red? What about, where are all the oranges and yellows and light greens and the cyans and turquoises and all that? They just don't show up like they do in real life. And as I put in the bar down here, a spectrum produced by a visual spectroscope is the purest, boldest spectrum you will ever see. And I am not kidding about that. I can't think of any other way to see a rainbow, I mean, not a rainbow, but a spectrum in all of its real true glory. In fact, even the boldest natural rainbow you've ever seen after a good rainstorm doesn't have the color saturation that you get in a visual spectroscope. And that's simply because the sun is an extended source. And so all the colors kind of wash out a little bit. And that's how inspiring this is. I mean, you think about the most beautiful rainbow you've ever seen and all of its colors, and then you look into a spectroscope, and there's just no comparison from a color standpoint, from a nerd standpoint. So that's where I'm coming from with this thing. And anyway, I think I should probably go to the next slide before I start talking like a fool for how excited I am about it. So this kind of begs an observing project. And I thought, well, here's a thing. In fact, professional astronomers have done this many times. You can get on the web and Google search spectra of all stellar classes or something like that, and find a number of sites where astronomers have put together spectra of a wide variety of stars from type O all the way through M, and even maybe in the deep, red dwarf categories. And what happens is, and this is incomplete, but what happens is you can start seeing these spectral lines develop and fade as you look across the different populations of stars. So we talk about an O star, which is a supermassive, super hot, 30,000, 50,000 Kelvin, super hot star. It's so hot that even the hydrogen lines aren't showing up all that well. You cool down a little bit into type B or B class, and the hydrogen starts to show up a little bit more. You hit Vega, 10 to 20,000 Kelvin, and now the hydrogen really shows up very well. I'm sorry I don't have an F star yet, but this is a project. So then you get to the sun, and something very interesting happens. Well, the sun, our favorite star, has a beautiful set of spectral lines in it, absorption lines, by the way. I know I probably haven't said absorption yet, but that's what these are. These are absorption lines. The sun has a beautiful set of absorption lines in it, and they're easy to see in a visual spectroscope, but they're dang hard to photograph because they're so low contrast. So here I'm showing the best of my abilities here to capture the solar spectrum safely, using the spectroscope in what I call standalone mode and looking at a reflection off of there's probably a glint off of a chrome tube of some kind. And it just, what happened to all the spectral lines? Well, they're there, but the contrast is greatly reduced, and that tells you something about the type of star that our sun is. I don't know what that tells me, but it tells me something. So then you get into the older, cooler stars, and now all these elements that are here in the sun really start to come through. And you get Aldebaran and Betelgeuse, and boy, these are very powerful lines. Shiat, M-type star, and Russell-Gethy. Again, these photos don't do it justice, but you look at these spectra and they just look bizarre. They're like almost indescribable curtains of color coming down through your telescope. And you just know when you look at this kind of a spectrum and you look at this OBA type of a spectrum, you just know that you're looking at physically very different things in the sky. A star is not a star. They're all different. Every star has its own fingerprint, spectral fingerprint, and this is the way that we decode those fingerprints. So there you go. That's my really my pitch on how 3D printing has changed the way I observe and really fired me up very late into my astronomy career. I got a couple more slides. a quick note on manufacturing a Spectre. You know, it's not enough just to have a 3D printer. You got to know how to deal with making gratings. You can't just go purchase something off the shelf. I mean, you could, but maybe it would be very expensive. So I make them myself. And there's a hologram kit from liddyhollow.com that you can buy and make your own holograms. And with some knowledge about how to deal with all the subtleties in recording holograms, one can put together an exposure setup that creates gratings instead of pretty 3D images. And that's what I'm doing. Make the hologram, glue it onto a prism. I've got a Grism, and then pack the thing into a 3D printed housing, add a Barlow lens, put in your 1¼ eyepiece, and you are on your way. It works in 2-inch focusers. It'll also work in 1¼ but only on SCTs where you can really drive the focal plane out of the telescope by quite a lot. So, or pull it in quite a lot. Which way is it going? No, push it out quite a lot. Yeah. You know, it's a bit of a versatile instrument. And I promised you that I would tell you what I would do different, and here it is. So, future improvements, or what might I do different? If I was really trying to make a scientific instrument that we would record spectra and calibrate the wavelengths, then one thing that's super important is to have some sort of a reference that is always the same no matter where you point your scope. And the way to do that is to get light to just leak through without hitting either the prism or the grating, and just show up as a line adjacent to the rainbow. And this will always be at a fixed position. In my design, it's at 555 nanometers. And once you know the position of this thing, and then the position of one of the other lines, you can calibrate your sensor to give you all of the wavelengths of the other lines. And it unfortunately works in the standalone mode without the Barlow lens for me, but when I put it in my f5 scope, I don't see that leakage line anymore, and I can't capture a picture of it. Howard has done this at f4, and he does see the leakage line, so I think that's the hint. I probably need to open up some apertures somewhere, but I haven't done that yet. And you know, if somebody really wants it, I'll go and do that and make it work. The other thing is that if you really want to get into recording faint stars, you're going to have to take the cylinder lens out and let that spectrum show up as a skinny little line. All the light will be concentrated into a brighter beam, and you can have shorter exposures, and et cetera, et cetera. But when I do that, for some strange reason that I don't understand yet, the absorption lines aren't straight anymore. They're little chevron shapes. Here's a blow up over here. And that tells me that I have some sort of aberration either in the alignment of the optics, or you know, these are just off-the-shelf optics. There may be some flaw in them, or maybe it's in the recording of the hologram. That's probably the most likely thing, is that I don't have perfect beams on my hologram yet. But boy, for a visual scope, it doesn't matter anymore when you put the cylinder lens in, and these lines then become straight again. So it's a bit of a mystery, but again, it's a visual device, not a quantitative scientific instrument. So there you go. Thank you very much, and I will take questions. And I'm going to start looking into the chat here and see what you all got for me. So I was warned that there would probably be a lot of stuff for me to catch up to here. So bear with me for a second.
And please enter any questions you have into the chat facility.
Yeah. Okay, here we go. I want to get into full screen mode, which somehow I got out of. Boy. Where's the chat? There's probably a bunch of questions right there, and I'm not seeing them yet because I've lost my meeting controls. Where are they? Okay, Mark, you might have to take over. I'm sorry.
All
We
right.
knew that this might happen.
Sure. So I think, okay, so the first question I see is, it's just a pretty lengthy chat record tonight. I believe the first question was, what model printer do you have and how large is your print bed?
So it's a Prusa i3 Mark III, and the print bed is about 8 inches square. You can't go all the way to the edges of that, but you get the idea of the scale. There are a lot of printers out there in that size or that class at quite a wide variety of price ranges and capabilities. I highly recommend the Prusa. Okay, next.
So we had a couple other participants respond to this question, but I'll go ahead and ask you as well. Is it useful or necessary at times to finish parts after you take them off the printing table? So do some machining or something along those lines.
Yeah, well, that comes with experience. The idea is to minimize that. If you're doing a lot of printing, unavoidably, some parts have to have support structure, which you're just going to get in there and grab and crack off manually or with pliers or something like that. Usually, that's about all it takes. On both of these things that I just described, they have threaded holes, which are, it's nice to clean them up with a tap. But in general, on most 3D printing, you've got a very minimal amount of cleanup. And if you have to go in and machine something after you've made a 3D print, then I would suggest that you probably haven't thought of the right way to print it yet. Because you shouldn't have to machine anything given a decent 3D printer. That's kind of the point. So
if you go back a couple slides, people were kind of wondering, you have some y-axes labeled as well as the x-axis in your spectra. And people were wondering what the significance of the units on that y-axis.
Okay.
Slide 30.
So I'm trying to get there. What I need to do is I need to stop the presentation mode. Bear with me for a second. And let's see. If I close that and I close that. Come on, cooperate for me, please. It's just there we go. Okay.
So slide 30. Yeah.
Slide 30, thank you. Okay, get my mouse over there. I do Zoom for a living now, it seems like, and it's just so different when you're actually presenting. Okay, here we go. The y-axis is, these are gray level counts in the camera, and they're utterly meaningless unless you have some sort of photometric calibration that you can relate them to. So it's a relative brightness scale is all it is. And, it's not my intent to ever extract any meaningful data out of this stuff, but I just thought it would be fun to just play astronomer with it and see what I could do. So there are people in this club who have a lot of experience with photometric and wavelength calibration of spectroscopes, and they're not using slitless spectrographs like I am. They're doing it the right way for getting quantitative data. So
great. So Ed's wondering if you'll be selling kits for people who have their own 3D printers.
I knew that question would happen, and I'm sorry, but no. I've invested so much time in this. I am absolutely happy to print and assemble stuff for you for a price. It's just it's not something I'm going to release out into the wild.
So Richard made a comment. He said there's a great program called RSpec that would help you calibrate the spectra that you've captured.
Yes, thank you. I'm aware of that. And Richard is one of those guys who knows what he's doing. And maybe someday I'll be up to speed. Yes.
So Wes is wondering what the approximate star magnitude limit would be to see a decent visual spectrum in, for example, a 12.5-inch scope.
Well, 12.5 is exactly what I have. And unfortunately, due to this pandemic, I have not had a good night out in the dark sky yet, despite this thing being in my hands for over a year. So from in town, I live in deep southwest Lake Oswego. Deep southwest Portland, almost in Lake Oswego. You know, on a good night, I've got, you know, down to 4th magnitude, maybe, you know, visual. And with the spectroscope, I can confidently see beautiful spectra down to 2nd magnitude stars in town. 3rd magnitude, it's you know, it's a little more like looking at a faint fuzzy, I suppose. You can still see spectral lines. By 4th magnitude, it's like, well, I can kind of detect the broad features, but the fine details have started to disappear. I think out in a dark sky, I would be okay down to 4th magnitude pretty easily. And I don't know, I just have to push it. I haven't tried yet, unfortunately.
Okay, so we've kind of come to the end of the questions that were in the chat. If I missed any question, please ask again so that it appears at the bottom. Okay, great. Well, okay. So you're getting a few accolades. So Margaret said she loved your description of locating things in the sky.
Thank you.
Catherine is wondering what the actual product is that comes out of a 3D printer.
Let's see, that's a question that might trip me up here. What is the product that comes out of a 3D printer? Are you asking what kind of plastic, or because you can print almost any shape imaginable if you think carefully about how to print it. There's various kinds of plastic that are printed. Too many for me to even begin to mention, but I use PETG. The common one to get started with is called PLA, which is a 3-letter acronym for some large molecule. ABS, PVC, vinyl stuff. There's soft, flexible materials that are polyurethane based, and then you get into stuff that has various kinds of filler into it, and there's even stuff that that's metal filled with metal nanoparticles. That when you're done printing it, you got this plastic metal composite that you can then bake or sinter so that all the plastic burns off and the metal fuses together, and by gosh, you've got a metal part. It shrinks in the process, but it's a real thing, and you can do it at home. You're going to need a kiln to do the sintering, though. So I'm not sure what the question really was asking, but any shape imaginable, if you can figure out how to get it on the print bed, and quite a wide variety of different plastics. I hope that answers it.
And she followed up by asking how many dimensions something that you printed would have, and
all 3.
Right.
So I'm working on that 4th. That'd be really cool. Sorry for the sarcastic answer. I think maybe a better answer is, the maximum size of a part is going to be limited by the size of your print bed and how high up the travel is on your printer, and that varies. Mine goes up to, I think, looking at it right now, a little over 7 inches, maybe 8 inches. and the print bed is about 8 by 8. So you can print inside of a cube, pretty much anything up to the limits of that cube. So.
Margaret's wondering, so someone mentioned earlier in the chat about fumes that come from 3D printers, and Margaret's wondering what you might have to do to use one indoors.
So I have one right here next to me in this spare bedroom that I call my office, and I use PETG, which I have not I nor my highly sensitive wife have ever detected fumes coming off of that material. ABS, on the other hand, is quite another story. That stuff stinks, and generally people printing in ABS are doing it because they need the strength of ABS, but then they'll have to put their printer in an enclosure and vent it outdoors with a fan. And I see that all the time. OIT has a rack of 3D printers in their lab, and they do that. And you don't smell anything if they vented it properly. So you do have to be careful of that. And generally, the common easy to print stuff is generally fume-free. So PLA, PETG are great ways to get started in 3D printing, and I don't think you'll ever notice an odor coming off of them.
And a couple, Robert Wood and Ed Stroh mentioned that just what you said, that PLA and PETG don't generate fumes that are problematic. And then Ed pointed out that ABS fumes are toxic. So it's very important to be careful if you're printing that.
Yeah.
Howard is wondering how long it takes for a printed object to cure, and whether that depends on the type of feedstock that you use.
So curing isn't exactly the right word in the case of what I'm doing here. That does apply to a different type of 3D printing. But what happens is this filament is heated until it melts. It comes out as a thick liquid, just like hot glue does out of a hot glue gun. And then it cools almost on contact with the print bed or the layer you're printing on top of. And it just hardens, right, by temperature. So there's no curing time involved in that respect. It'll take, depending on how big the object is, it might take, a small object the size of your thumb might be a 20-minute print. Something like a Quinsite is, most of a day. And, people have done things on printers this size that are multi-day prints, depending on how complex and how big they are and what you're trying to do with it. So now the curing point, there's a whole different kind of printer that uses UV lasers to cure a photopolymer. And you actually have a little pool of photopolymer instead of a print bed, and your laser will either scan or go through an active matrix display and put an image down onto the surface of that photopolymer, cure that layer, and then that layer will step down a little bit. There's actually a print bed under it, and print the next layer and print the next layer by curing. And I don't know what the cure times are on those, but I have seen one in action, and to me it looked like it was printing at about the same rate as one of my prints over here. So it's probably a long answer to a short question, but that's the best I can do.
So Jim is wondering how complicated it is to maintain a 3D printer and whether or not there's constant cleaning involved.
That, I think, was probably my biggest fear in getting into 3D printing. And probably because Bob, he's always telling me, well, I had this problem last night and here's how I fixed it. He's just all excited about it. And I'm like, well, okay, that's great, but I don't want to do that. Well, it turns out that the Prusa is really a pretty low maintenance printer in my experience. I think the other part of it was that I bought it as a kit. So I had to put together every nut and bolt and put all the motors together and all the drive belts and all the hardware and plug things in, and in the end, I know exactly what's inside that printer. And I've had things go wrong on occasion, and it's like, oh, I know I have to take these 2 screws out and pull something off the print head and get to that filament that got all bound up inside there. Cleaning is, you keep your print bed clean. That's easy to do with a little warm soapy water or alcohol. And the nozzle itself is super important to keep clean. And that's just becomes a matter of habit. Before you start a print, you inspect your nozzle and make sure there's not a lot of leftover plastic all gummed up inside that thing. And the way to clean it is you heat up the nozzle and you grab a pair of pliers and just gently pull off the stuff that's hanging from the print head. On occasion, I need to change the diameter of the print nozzle. You can have large bore print nozzles or small bore print nozzles. Those require that you heat up the nozzle to a temperature that is dangerously hot to touch. So you're going to use a wrench and you're not going to touch anything as you loosen up that nozzle. But it really is far less maintenance than I think I was worried about. And, I think some of it is just you got to be diligent about how you treat your printer, and it's not a hammer you can just throw in the garage. So treat it nice, and it'll treat you nice.
Jim is wondering if you could tell us anything about the 3D printer on the International Space Station.
Oh, I know nothing about that. That sounds like an internet search for somebody.
So I will say also that there is a professor at Portland State who is, I think he's the main person behind developing that 3D printer. So
Nice.
There's somebody local that you can contact if you really want to learn more about it.
Yeah, space qualifying a 3D printer, I'm sure, was not an easy task. In fact, my company, we have this big giant refrigerator-sized 3D printer in a lab, and it is used for, important jobs that require, some sophistication, and there's a long queue to get in line to get anything printed off the thing. But in the optics lab, it's like, you know what? I can't position this optic on my table with the Newport hardware that I've got. I just wish I could 3D print something and put it where I want it. And so we got ourselves a 3D printer a few years ago, and we were all charged up about getting a Prusa because we liked it so much. But the darn thing isn't UL listed, so we couldn't buy it and put it into our building because it was against company policy. So we had to buy a $4,000 printer for the UL listing. And you know what? That darn printer in the optics lab has given me more trouble than my Prusa here in my bedroom. And the price difference is a factor of 4. So, it could be familiarity. It could be just subtleties that I don't understand about that other printer. I'm not going to say what name it is. Because it's a damn good printer if you know how to use it, I'm sure. But God, getting the plastic to stick to the glass print bed can be just mysterious sometimes. Why isn't it sticking? So.
So Jim is wondering roughly how much it might cost to print something.
Well, you can go online. This is how I got started in it. Was I designed something in SketchUp. The very first Quinsight, I did it in SketchUp. It was not easy. I think I tried some other practice things first, and I used Bob to try to print some things, and so I kind of got familiar with what I was doing. And then when I was really ready to make a Quinsight, I went online to 3D Hubs. And this was 3 or 4 years ago now, and I think things have changed a little bit. But they were charging me like for a set of that stuff, $40 or $50, I think. And that was for me, including for me to go pick it up from their place. so it was kind of expensive. I mean, very expensive, really. Whereas that same thing cost me in material, you know, just a couple of bucks of material is being squirted out on that print bed. So it's much more cost effective if you're going to do 3D printing to get your own. But it's really, I think, very empowering to know that if you want to get started in it without investing in a printer, that there's ways to get your designs printed. They're going to cost you more, but you'll get a sense of what you're doing, and that really can open up some doors for you depending on what you're trying to do. So.
Okay, and Frank is wondering if you know anything about software related to 3D printing for Mac computers.
Oh, I'm sorry. I am not a Mac guy. Maybe somebody else can answer that, but I don't even know if Fusion 360 has a Mac version of it, but I'm sure there's stuff out there. I just don't know what it is.
And I see that Ed put an answer. Oops.
Oh,
He
good.
put an answer in the chat.
Okay. Oh, I finally found the chat window. You warned me. You're right. Okay. Yeah.
So Jeff says Fusion 360 does work on Macs.
Oh, good. Okay. I'm not surprised.
Okay, so I think we've reached the end of the questions again.
Okay. Thank you so much, everybody. Those are great questions, and it was really a pleasure to present this to you all. And I hope people got a lot of good stuff out of it, and go try printing something someday.
So Margaret's
How can we
asking,
contact me?
yeah.
Yeah, so I had my website up on the slides. If you missed those, they'll be out. But I will just go ahead and put my email right here in the chat, r2d2b2@comcast.net. Sent. There it is, everybody.
We'll also be posting the recording of Rob's presentation, and it'll be available through the club website sometime in the next week or two.
Awesome, thank you.
So thank you very much, Rob. That was very interesting. It was nice to see everybody. I hope you can join us again next month.
Thank you, Rob. That was great.
Thank you.
All right, thanks, Margaret.
Hope everybody's doing okay after the storm. Take care, and we will see you again next month, hopefully.
Okay, bye-bye.
Thank you.
I'll stay on. I'll stay on here as long as you guys have the site open. So I don't know how this works in the end here, but I won't ditch you until everybody else is gone.
Okay, it's up to Mark.